Hi, welcome back to Unit 6 of AP Physics C. In this video, we're going to look at the first of the specific type of oscillators, and that's going to be the mass spring system. So I know in most of the pictures you see here, the springs are vertical, but you can always just have just as much as it being a horizontal spring as well, or a spring resting on with a block resting on the table and allowed to oscillate back and forth there. All right. So a mass spring system consists of a mass that will stretch or compress the spring. The spring, again, wants to restore back to its equilibrium position. And so one thing that you need to really focus on in the mass spring system and the pendulum is what is that restoring force? So in this case, the restoring force would be the spring force. And if you remember when we talked about forces, the spring force is F equals negative Kx, right? Or K delta X. Now, this will allow us to do a little bit of a calculation or a little bit of an idea of like, okay, what is the acceleration going to be? So essentially you just said that equal, like if it's on a spring or if it's on a horizontal, your acceleration would be simply negative Kx over m. If it's hanging, you would have to account for the weight of the object. And so it actually ends up being negative mg, or sorry, a lot of times in these we don't worry about the negative sign, so it would be Kx over m minus g would be your acceleration. So this is your horizontal system and this is your vertical. Okay, and that's going to come into play, especially when we look at the example problem where we're deriving the period equation. But something that the AP test and Physics C do is what you see these combos. So they'll put springs in combination. And so when a spring is in parallel, so this one over here is our parallel set, you have to find the effective spring constant of the system. And one thing to note is that if the mass is being hung from multiple springs, every spring is going to stretch the same amount. And so what happens is your effective K value is just simply the sum of it, right? The sum of your spring constants. And that comes from the fact that the idea that they're all going to stretch the same amount. And so it's like you can factor the X out. If I have like, okay, what's my system look like? Well, this force is pulling all three springs down in that case. So this is pulling, K1x plus K2x, right, plus K3x. Well, if they're pulling it all the same distance, I can factor out that x, and I end up with like K1 plus K2 plus K3x, right? And that right there, the K1 plus K2 plus K3, that is our effective spring constant. Now, it's going to be a little bit different when the springs are in series, and the reason why it's called parallel, because you can see these springs will not touch. So springs in series, they're going to be connected end to end to each other, which means they're not going to stretch the same amount, right? Because each one has its own K value. So what you would need to do for each one is figure out how far does each one move. And so that would be F, but although they're going to have the same force applied to it, so that would be F over K1, F over K2, right? And F over K3. And so what happens is the effective spring constant is 1 over K1 plus 1 over K2 plus ... right? And so to get to your effective K, right, you would have to do that summing, right, to the -1, right? So you have to do 1 divided by all that. Now, one of the things I like to do on the test is to have you derive the period expression for the different systems, and those are the two example problems we're going to kind of look at, so you get used to this. One thing also I want to point out, there is a condition for simple harmonic motion, and I didn't talk about it in the first video when I should have. So the condition is that, sorry, I'm gonna go back to my notes real quick, that the second derivative of position is simply negative omega squared x. Okay, this is the condition of simple harmonic motion, and this is the reason why it's a trig function, because what's the only trig function that kind of returns this negative, self thing? Well, it's trig. Okay, so here we're going to derive an expression for the period of a mass spring system, and we're going to assume vertical, and I'll show you how you would adjust this for horizontal. Okay, so if we look at the free body diagram, we would have the spring force up because it wants to restore it back. We would have the weight of the object down, right? And that's what's causing the acceleration. And what that's going to do is that's going to allow us to do some substituting in, because that condition for simple harmonic motion, this expression right here, well, that's acceleration. Okay, that's all that is, right? Because what's the second derivative of position? Acceleration. And so once we get in here and we find an acceleration, then we're going to substitute in that omega squared x, right? Sorry, I dropped my paper. We're going to plug in that omega squared x for our acceleration. And so what we do now is say, okay, spring force minus weight equals ma. Well, spring force is kx, weight is mg, right? And then a, we're going to plug in that omega squared x. In fact, we're going to call it negative omega squared x, right? So if I quickly factor in that negative sign, oh, sorry, because this would be, right. Nope. We know that the object is going to accelerate up, so that's why we're going to plug in a positive omega squared x, right? So if I want, basically what I'm going to do is, oh, I was erasing. No, I need to solve this for omega squared. I need to solve this for omega. Okay, and so when I do that, now I'm going to divide everything by mx, and you can see things are going to cancel out over, when I split the fraction. So if I split the fraction, I would get k over m minus g over x, and that's going to equal omega squared. So omega will be the square root of k over m minus g over x. All right. And now I need to substitute that into the omega equation. So omega equals 2 pi over t. And so t would be 2 pi over omega. And so it's going to be 2 pi over the square root of k over m minus g over x. But what I can do is I can write that reciprocal in the square, so I end up with 2 pi square root of m over k minus x over g. Okay, and so that would be of a vertical system, right? Because we do have to account for the stretching, and that's what we're asked for based on our situation here. But if it's a horizontal, right, the only force acting on horizontal would be SP, right, the spring force. So you don't have to worry about FG. So that actually turns your period into 2 pi square root of m over k. So if you see, if you have a horizontal system, the only two factors would be mass, and the mass of the object, and then the spring constant. But if you have a vertical system, it's the mass of the spring constant, and how far you stretch it, as well as g. Okay, so those are the expressions for the mass spring systems period. In the last video, we're going to look at the pendulum and the different types of pendulums we can encounter here in this unit.